All right, ladies and gentlemen, it is currently 5 o'clock at Dallas Grimes High School, and I am ready to go home. So hopefully this will go smoothly, but I am tired. So if I make a couple mistakes, hopefully I will catch them and fix them for you as we're going through. But we should get through this in, I don't know, 20 minutes or less. Let's see if we can get moving. First things, we have different types of reactions that we're going to be looking at, and here's just a brief outline of them. And do it this way. Um, don't get too confused about all these. They're just really general types of reactions that you should be able to kind of rationalize out once you start looking at them and they're not all thrown at your face all at once. The metal replacement one, that's what you did in the lab. The metal acid, also did in the lab. We have three different kinds of neutralization reactions. I know there are only two listed here, but this acid base splits up into two. So in a net ionic reaction, the things that has to stay in, that cannot be canceled out, are things that are solids, gases, liquids, or unique aqueous solutions. Unique aqueous means that they do not occur on both sides of the chemical reaction. So what gets canceled out, the only thing that ever gets canceled out is when we have the exact same thing on both sides of the chemical reaction, and they are aqueous. Here's kind of I guess, the most common type of net ionic reaction where we have two different reactants forming two different products. It's a double replacement, and this you would be asked to predict the product. So the potassium is going to replace the magnesium, and then you have to determine what is going to be a solid, if anything. What's the precipitate that forms? So we have magnesium phosphate as our precipitate. And so when we split this thing up into an aqueous solution, everything's going to split up except for this. And I should note here that in this PowerPoint presentation, if I do not indicate what the state of matter is, we are assuming that it is aqueous. All right. So if we split things up, we end up with this total ionic reaction. And a couple things about this that I want to point out. First of all, we see here that we have potassium with the lowercase, the subscript 3. This 3 indicates bonding. When it dissolves in water, we no longer have that potassium bonded with the phosphates. We have those three different potassium ions all separated. Since we have this 2 coefficient, we end up with a total of 6 potassium ions. So that's where that 6 potassium ions comes from. We also have 6 on the other side. And guess what? Those are going to cancel. The other thing that cancels here is our 6 nitrates. 6 nitrates. Oops. So what we're left with is our magnesium and our phosphate. Makes our magnesium phosphate. There's our net ionic reaction then, everything that I circled. What's going to help you when you're doing these, like I'm going to put up this one up on the screen and you're going to look at it and maybe pause it right now and then do the problem yourself and then come back and see if the answer is correct. That'll be the most helpful while you're going through this PowerPoint. So the balanced chemical reaction for this though, calcium is more reactive than iron, so it's going to switch places. And we end up then with calcium sulfate, which is a solid. Sulfates are usually soluble unless it's with calcium. So we end up with that particular precipitate forming, as well as the iron metal precipitating out as well. So we end up with the total ionic of this, where we have iron and sulfate as the only two aqueous parts. Everything else is a solid. So this is a really interesting example where the net ionic is exactly the same as the total ionic. These are not common, but they do show up. The other one that's not real common is a no reaction, which should be something like this. Lead reacting with calcium chloride. Lead is less reactive than calcium. So lead will not replace calcium in this chemical reaction. There's my arrow. So no reaction occurs. And if no reaction occurs, say no reaction. In order to answer a question like this, you would have to have the activity series of metals, which would be provided for you. All right, going through this one. Now here's one with lithium and magnesium sulfates. We have another metal metal replacement reaction. So lithium will replace magnesium. So if you're going to do a problem like this, this is the time to pause. Here we go. Total complete reaction where we have lithium replacing magnesium to form the products. And we have it all balanced and everything's labeled except for the aqueous, which are assumed. Oops, this is a mistake. This lithium, or this solid here, ooh, get rid of that. That one's wrong. Let's see here. I'm taking way too much time to do this, but I want to make sure I make a very specific point here. That is, that's a really crappy black pen. All right, anyway, this is aqueous. That's gray, that's not black. Oh well. Pen color. Sure, we'll use green. All right, so split things up. We have our magnesium and our sulfate splitting up, and we have our lithium and our sulfate splitting up. So we have the only thing here that's going to cancel out is our sulfate. Not a fan of the green. We'll go back to red. So we have lithium and our magnesium, and then we have our lithium and our magnesium. So our net ionic looks like that. This is a metal replacement type reaction. Moving on. Single replacement using halogens. The first thing we have to do here is to determine if a reaction possibly could occur. So we end up with the activity series of halogens. Oh, it's still green, dang it. Increasing as we go up. So fluorine is the most reactive, iodine is the least reactive. So the thing by itself here, the single replacer, needs to be higher on the periodic table than the thing getting replaced. And since iodine is lower than chlorine, it will not replace chlorine, and so no reaction occurs. All right, I'm going to change the pen color here. Pen color, ooh, cyan. We'll do some blue, see how that works. Sodium chloride reacts with fluorine. So again, if you're going to try this one, this is a good time to pause. Here we go. Fluorine switches places with switches places with chlorine. So we end up with sodium fluoride and chlorine gas. These are our aqueous solutions again. And we end up with this ionic, where we end up with sodium and sodium on both sides. Oh, I like cyan. And we're left with our chlorine, our fluorine, and our fluorine, and our chlorine. So we have our net ionic made up of those. Ooh, my circles are getting better. I wish I had a tablet or something to draw on rather than using the mouse pad. It's kind of a pain. We end up with that. Now we get into the last kind of reaction that you did in the lab, which is a metal and a acid. So we have magnesium with nitric acid. Again, good time to pause. Here we go. Magnesium is going to replace the hydrogen, and we do have to be careful to make sure that it will actually react with acid. Some of the metals like mercury or copper or some of the very silver unreactive ones, they don't do this reaction at all, so there'll be no reaction. What this one does, we get magnesium nitrate and hydrogen gas. Split things up accordingly. Strong acids get split up into their two parts, hydrogen and nitrate, and then we have our hydrogen gas staying together and listed because it is a gas. Remember that gases do not get canceled out. Neither do solids. So what we have here is the nitrates canceling out, and that is it. So here's our net ionic. Our magnesium metal reacts with hydrogen ions to form magnesium ions and hydrogen gas. Oh. Now we have our neutralization reactions. So this gets into the very last stuff that we need to do examples on. We have our strong acid, strong base at our beginning. So strong acids, remember the six: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, perchloric. And then we have strong bases are defined for us at this point in our chemistry careers as anything that ends in a hydroxide, an inorganic compound that ends in hydroxide. We end up with that. This is the first time we see liquid. Recall now that liquids do not get canceled out in the net ionic. It has to stick around. It does not split up. So the total ionic, we have our strong acid splitting up completely. There's the strong acid. We have our strong base splitting up completely. There's the strong base. And we're left with then the nitrate splitting up completely and the water. So if we start canceling things out, we have our nitrates. We have our hydroxide stays. Sorry. We have our aluminums canceling out. So we're left with hydrogen, hydroxide, and water. Our total ionic is that. This is important. Anytime you have a strong acid, strong base, if you can recognize your strong acid and recognize a strong base, your net ionic reaction will always be the same. Hydrogen ions plus hydroxide ions make water. And looks like there's a typo on this slide as well. There should be a 3 here and a 3 here. There we go. Next one here is when we have a weak acid, which becomes a little bit more tricky. Sodium hydroxide is definitely a strong base. Then we have oxalic acid, which is a weak acid. The oxalate ion is one that you are supposed to memorize, but is not often used. It is this. C2O4. It has a -2 charge. We have our sodium hydroxide and our weak acid. Now, weak acids, since they do not dissociate 100% in an aqueous solution, do not get split up when you write out the net ionic or the total ionic. So we have here our weak acid and our weak acid. We do have, however, our strong base separating. So the only thing we can cancel out are sodium and our sodium. So we have our hydroxide part of our base. That forms our water. So we have our hydroxide and the acid component, that hydrogen, forming our water. And we're left with the oxalate ion. So our net ionic is this. Our oxalic acid, our hydroxide, makes our oxalate ion and water. This will be true for any kind of weak acid, strong base. The weak acid will stay the same. You'll have your hydroxide. Whatever that ion is, that's part of that weak acid, and water. And finally, our last one, our neutralization reaction. We have calcium carbonate and sulfuric acid. Now, I purposely chose some of the messier ones. There are definitely simpler examples that we could work through. But if you can do something like this and navigate through this oxalate ion and not be afraid of that, that's going to be better. So we have the same thing here. We have sulfuric acid. We could have used hydrochloric acid, which would be a little bit neater, but we want to kind of throw you in the deep end here a little bit and make sure that these sorts of things also make sense. So here we go. Here's the balanced chemical reaction. Anytime we have a neutralization reaction, we end up with water and whatever's left. We have water and whatever's left. Making sure you predict those chemical or those products correctly. Whenever we have a neutralization reaction between an acid and a carbonate, we produce water, carbon dioxide gas, and whatever's left. This one's also interesting again because one of the products here is a solid. All right. So, total ionic. The only thing that we can split up in this case is going to be the hydrogen ions and the sulfate. And if we look at the other side, then we can see there is nothing whatsoever to cancel out. No sulfate over here, it's bonded, no hydrogen. And so the net ionic is going to be the exact same thing. This really just keeps in the tradition that liquids are left together, gases are left together, and calcium sulfate is kept together. Take a moment and try this problem and see what you end up with. I don't have the answer made, but let's get rid of calcium, and instead, this is going to be difficult using the mouse pad, but let's do lithium carbonate and see how that changes. Keep in mind that when lithium becomes lithium sulfate over here, it will be soluble because all alkali metals are soluble. All right, well, just a few closing remarks and then we'll be done. Don't forget, when you watch this, put your initials down in the YouTube comments so that I know that you actually watched it. And boy, I should have like a quiz or something too. I don't know. I'll think of something. Oh, hey, here's another one. Sodium. I didn't know this was on here. This is fantastic, ladies and gentlemen. Sodium hydrogen carbonate, also known as sodium bicarbonate. Sodium bicarbonate is baking soda. So we'll go through this one quickly. So we have our sodium bicarbonate. Again, any kind of carbonate is going to produce our water and our carbon dioxide. And this one's a little bit similar to the example I told you to try with lithium, where we end up with sodium nitrate here being an aqueous solution. So we've split this thing all up and we end up with several things that are aqueous. Our sodium and our bicarbonate ion, that's what this would be called. And then all of our products, keeping in mind that the only things that stay together on this side now, since sodium nitrate is aqueous, is the water and the carbon dioxide. So sodium cancels and nitrogen or nitrates cancel. And we end up with hydrogen plus the bicarbonate ion forms water and carbon dioxide gas. And there it is. All right, now here's for some closing remarks here. First of all, in order to do these things correctly, a couple of things that you have to be comfortable doing. First of all, predict the products correctly. And this is one of the things or one of the outcomes of that initial naming quiz that you had to score 95% or higher on. To be able to predict the products correctly, you have to know the states of, or the oxidation states that they'll form. Make sure you identify what species cancels, and these are the aqueous ones that are on both sides of the reaction, and cancel them out. You are right now to the point in your chemistry career that you should be able to do these two things. Finally, don't forget the charges. In order for these things to be correct, you have to communicate your answer fully, and that includes charges. And that is it, ladies and gentlemen. Hopefully that took less than 20 minutes. I have no idea. I haven't checked it yet. But this is Mr. Mangler wishing you a good night.